What's up, everybody? My name is Jacob, and this is a quick tutorial on how to simulate a robot using Atoms. Atoms is an MSC software. It's provided free for students. This is the student edition. So essentially, we're going to learn how to import a model made in SolidWorks into Atoms, simulate that model of your robot, and also analyze the post-processing results. So what we'll be able to do at the end is import the robot. This is one that I made of the UR3 in SolidWorks. Import that to Atoms, make it do some kind of movement, and then also be able to pull up the post-processing results and analyze those. So here we're looking at the torques of each of the joints. So we'll close out of this and we'll get started. So we'll open up SolidWorks, and you can see we opened up to an assembly of a RRR robot. So 3 revolute joints, 1, 2, 3. And you can see that I've constrained it to this floating block, and it's just going from one corner to the other corner. This robot might be doing something such as laying down glue or welding. So this model was made completely in SolidWorks. It's 4 parts. We have the base, link 1, link 2, and link 3. So before we export this, just pay attention to your orientation. So in this case, my base is along the XY plane. Your materials don't necessarily need to be defined yet in SolidWorks because we'll do that later in Atoms. So starting off, you have your model. Go to File, Save As, rebuild it when it asks. And we'll save this to the desktop, and we'll save it as Robot 1. And we're going to save this as a parasolid. Note it's the parasolid.xt. And save. So that's all we need from SolidWorks. Now we're going to open up Atoms View. This can take a few seconds depending on the machine, and like I said, this is an MSC software, and this is the student edition. To get that student edition, all you need is your student ID card and send it to them. Then they will send you the license and download instructions. SolidWorks is also a free software, and so is Inventor. So now we're in Atoms. First, we're just going to click New Model. We'll name it Robot Tutorial. Click Apply, click OK. So now we're on a blank canvas. Now we're going to go to File, Import. This is where we import the file that we just saved over here on our desktop. So change the file type to Parasolid. Double click File to Read. Go to Desktop, Robot 1. This is the one we just saved. And open. Next, double click next to model name. Click Robot Tutorial, click OK. That'll add the name. Note that it has this period before the name. Click Apply and click OK. So you can see real quick that Atoms has successfully imported our model. Right now it's in vector form, so click this sphere down at the bottom, and that makes it into a shape that's a little bit more visually pleasing. Some quick controls. To zoom, press Z on the keyboard and move your mouse up and down to zoom. To rotate, press R on the keyboard and click the left click and move that around. To translate around the screen, just press T and you can move the robot. One more visual change I'm going to make is I'm going to change the colors of the links. So you can see here we have the base, link 1, link 2, and link 3. There shouldn't be more than one solid except for this base, because it has solid 1, which is this base part, and solid 2, which is this. So it looks like Atoms might have imported it twice. So I'm just going to go ahead and delete these extra ones. Close, delete. What is going on here? Okay, now that everything is deleted, I'm going to change the colors of some of these. So click your solid, click appearance, and we'll change this to double click, and we'll say just coral. Sounds like a nice color, and you can see that changed the color of this. And then we'll also change link 1's appearance just so you can tell the difference between the 4 elements of this. And we'll change it to science. So double click, apply, okay. So here is our robot. Again, just press R to rotate. You can see we have the base and all of the links imported. So the next thing we need to change is gravity. If you zoom in, you can see that gravity is facing along the negative y axis, and that is not right. So to change that, just go to settings, go to gravity, and instead of having gravity in the negative y direction, we'll have it in the z direction, and click OK. So now you can see that gravity is now facing downwards. Cool. And zoom out. Alrighty, so we've imported it from SolidWorks as a parasolid. We've changed the colors. So next, we need to set the material properties, and to do that, just go under bodies and click one of the first bodies. So we'll click base, click modify, define mass by geometry and material type, double click material type, and for this we'll just use aluminum. When you're doing a more accurate simulation, make sure to identify the correct material type, and that'll give you the correct weight, center of mass, etc. So apply, okay, and we're just going to do that for all 4 of these. Aluminum, okay, modify, geometry material type, aluminum, okay, apply, okay, and modify, geometry material type, aluminum, okay, okay, okay. Check this last one, make sure we did that, and we are good. So now we've imported it, added material types, and now I believe we are ready to do the joints. And before we add joints, and what I mean by joint is in SolidWorks when you're mating parts together, you might do like a revolute joint or a prismatic joint. We need to do that again in Atoms because it doesn't know what the relationship is between these links and the ground. So to simulate, we're going to show a simulation real quick, just because I think that's valuable to test whether or not the design decisions or assigning decisions that you made make sense. So all you really need to pay attention to right now is the end time and the steps. So this 5 seconds means that our simulation is going to last for 5 seconds, and it's going to take 50 steps. So if I run this, you see everything just fell. That's because we haven't assigned any kind of joints and no fixed geometries. And because of gravity, the whole thing just falls down. So we'll be coming back to simulation relatively often because I think it's, again, a valuable tool to make sure that your assigning of joints is correct. So we're going to start off bodies. We already have bodies because that's just what we imported from SolidWorks. So we'll start off in connectors, and the first one we're going to use is a fixed joint. So go ahead and click fixed joint, click the base, click the ground, and then it'll allow you to choose a point. And so just click that point. So what we just did there is added a fix. So you can see there's a little lock there. Let me zoom in a little more, maybe you can see that better. So you can see a little lock, and that indicates that you have successfully fixed that joint. We'll also fix this floating piece here. Same technique, click out, click the piece, and then click the point. And we'll just do that one more time just to make sure. So we'll click the base, click the ground, and we'll do a fixed joint at the bottom here. You don't necessarily need to do that many, that's just for safety and to make sure that it's properly constrained. So now that we have our fixed geometries, if we go back to simulation, we can run it again, and you'll see that the fixed geometries that we just fixed don't move anymore. It's because they are now fixed and gravity is not pulling hard enough. So we are now still looking at connectors. So our first 3 joints, they're considered joints, although they're just fixed geometries. 1, 2, 3. So let's add another geometry. So we don't have any prismatics, we just have 3 revolutes. So we'll use this hinge, and it says create a revolute joint. So just click that, and it pops up with the revolute joint menu, and it says 2 bodies, 1 location. So it's a similar way of assigning to the fixed geometries. But notice it says normal to grid. So when you create the two bodies and select the location, what it's going to do is create a revolute joint normal to this grid down here. Okay, so I'll click the base, and then I'll click link 1, and then I get to choose where that revolute joint is. And so I just put it there. And if we zoom in and rotate around a little bit, so now you can see that hinge is right there, and that's a joint between the base and link 1. And I'll zoom back out. So we're going to do that again with the other two. So that's joint 4 is right there along that first joint. So click revolute again, but this time we're going to click pick geometry feature. This gives you a little bit more flexibility on the orientation of the joint. So we'll click link 1, click link 2, and then we'll click the center of the joint. And now you see it has this arrow coming out. This is allowing me to choose the normal axis of rotation. So I'll choose normal, of course, along the joint axis. And if I zoom in, you can see that that Adams has created the joint along that axis of rotation. Okay, so let's just do that one more time with the joints. We'll click link 2, click link 3, click the center. You might have to rotate a little bit to get that correct center. Click, click, and center. And since we're still picking a geometry feature for the normal axis, we'll rotate it a little bit, and so now we have our geometry along the axis. We can zoom to verify that. Cool. Alrighty, so now we have assigned our fixed geometries, assigned our joints. So let's simulate this one more time to see how we did assigning joints. So you can see, let's slow that down a little bit. To slow it down, just add a few more steps. Maybe we'll go to like 1,000 steps. Rewind. So now it's just going a little bit slower. You can see that we haven't defined any other elements. So it's just the 3 joints moving around, and we wouldn't expect joint 1 to move at all just because there's no forces going in the X direction. And so we'll stop, go back. So that just indicates to us that we assigned the joints correctly. So the next part is to add the motions. But before we do that, let me change up the icon settings. And the icon settings are these markers here. You can see it says markers, as well as the joints. So I'm going to specify attributes for the joints, make sure they're on, and I'm going to change them to be real big so you guys can see them easily. So now you can see that I did that. You can see the joints sticking out of each of the respective elbows. You can see the fixed geometries. Again, you can see gravity facing down. Okay, so let's add some motions. So we don't have any prismatic joints, but we do have rotational joints, revolute joints. So click revolute joint under motions, click joint 4, which is joint 1, and that's going to add your motion there. So we'll just do that for each of the 3 joints. Alrighty, so now we have joint 4, 5, and 6. Those are all the revolute joints, and if you look under motions, we have motion 1, 2, 3. Okay, so if we go back to simulation, we can simulate this again, and now you can see that it's not just moving all over the place, it's actually moving according to the motion that we just set. So I'll stop that, and let's take a look at the motion that we set here. So name is motion 1, it's on joint 4, which is right here because of the 3 fixed geometries. But what we're really worried about is the function. It's a time function. So right now what it's saying is it's going to move 30 degrees along the time. So over however many seconds, 5 seconds, it's going to move 30 degrees. But we're going to change that. So we'll go back to motion 1, modify, and what we're going to use is a step function. So type step time 0, 0, 1, maybe 3, and then 30 degrees. So to explain this step function, it's a step function with respect to time. This first element here indicates when the step function starts. So 0 means that it's going to start immediately. This 3 here is indicating how long the function lasts. So this one lasts 3 seconds, and this last element indicates how many steps it's going to take. So, or sorry, degrees. So this says 30 degrees. It'll go 30 degrees over 3 seconds, starting at the beginning. Apply, 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 and let's simulate that again. See how that looks. So it's difficult to see, but it's going over 5 seconds. You can see that it's going 30 degrees here over the 5 seconds. So we'll stop that. For right now, we'll only worry about 3 seconds, and we'll make that go a little faster since we'll be coming back to that pretty often. Alrighty, so in the next step, we can go back to SolidWorks actually. And SolidWorks, in this model, you can use the measure tool to measure the relationship between different elements. So you can see here the angle between link 2 and link 3 is 61.97 degrees. That's probably not exactly right since it's not at the very edge. But by doing this, you can see what the angles are at the beginning as well as the angles at the very end. So instead of watching me do that, I did that all in SolidWorks, or I'm sorry, I exported that all to Excel. So what to look at here are these 3 columns. So column 1 this is joint 1. So joint 1 starts at 0 degrees and goes negative 14.33 degrees. Joint 2 starts at 30 degrees, as you can see here, and goes to negative 24 degrees. Joint 3 starts at 60 degrees and goes all the way to about 90 degrees. And you can see this last row here is essentially the change in angles. So we're going to be using those in our step functions. So the first one is 14.33 degrees change. So we'll go to motion of joint 1, modify, and let's just put this to 14.33. And I'm just going to copy this so I don't type it out every time. Apply, OK, apply, OK. Motion 2, we're going to do the same thing. So just type in your step times 0.003 seconds. And for joint 2, we said it had a change of negative 5.55 seconds. So, or sorry, degrees. 5.55. Apply, OK. And we're going to do that one more time for the motion of joint 3. So copy that in. 3 seconds is the duration. And going back to our Excel, it started at 60, went to 89.5. So that was a change of 29.5. So we'll do 29.5. Okay, 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 okay. And let's get out of this. Go back to settings. You can get rid of your icons. Just turn them all off. It's probably a good idea. So that's a little cleaner. And let's simulate that. Oh, that's going way too slow. Let's go back to 50. And simulate. So now you can see the joints have moved it's moved the 14.33, it's moved 5.55 and 29.5. And if we rotate, we can see that that made it to the end of the square. Let me change the color of this one real quick just so you can see it a little better. Modify, appearance, and we'll make that some kind of, I don't know, clay red. That sounds nice. Okay, now we can see that. Let's rotate to the top and let's run this again real quick. So we can see the robot is going from the initial position to the end. So that is really all there is to simulation, and you can see just with those simple steps you can probably apply these kind of techniques to anything from the UR3 like you saw in the beginning to automobiles to really any robot that you can imagine. So the last thing I'm going to go over is post-processing. So let's simulate this one more time. You can see it starts at point A and goes to point B along the line. So post-processing, essentially these are results. So go to results, post-processor. And So what you need to look at is this bottom area here. So look at your model, that's the robot tutorial that we imported. Filter lets you decide what elements you want to look at. So the body lets you look at the links. Forces would let you analyze the forces, but in this case we don't have any. And the constraints is all the joints as well as the motion. So let's look at the link 1. So what we get here is by clicking on link 1 of the body of the model, we can choose different characteristics of link 1. So maybe we want to look at the velocity of link 1. So we'll just click the magnitude, add curves. So this is link 1 velocity. It starts at 0, goes to 15 millimeters per second, and then goes back to 0. And that's kind of what we expected. It slowly starts up and ends. But we can actually add all these if we want. So add curve, add curve. We can see that that link 3 is actually moving the fastest, and that's something that we'd expect because it's so far out from the center of rotation. So to clear it, just clear plot. What else can we look at? We can look at angular acceleration, potential energy, but that's all up to you really. So joint 1, 2, and 3 are fixed. Joint 4 corresponds to this joint here. So we'll bring that back up. So the joints are really one of the most important elements to look at. So we can look at the angular velocity, make sure to hit magnitude. So you can see the velocity of that angle. You can see the acceleration if you want. Clear those. The element torque is a really good one to pay attention to. So you can see that it starts off a little bit with less torque and works its way up to towards the end with significantly more torque. We can look at joint 5 and joint 6. So you can kind of see how the torques of each of these is comparing to each other. So that's post-processing. As you can see, there's a lot of characteristics for really any component that you want to look at. Really completely up to you. So just play around with that. The torque is probably one of the most valuable characteristics to look at. But again, whatever your objectives are, you could probably find it in atoms. So again, that was a quick simulation of atoms, simulating a robot using MSC's software. Cool. Thank you so much.